Yeah, no, it's difficult during the pandemic period. We lost this opportunity to interact in person, so through Zoom, yeah, I think we try to do our best to make it a little bit more engaging. So, how many students in this course? I just want to get a rough idea and when I can also start. So right now we have 13, 14.
Yeah, I think typically it's around 20 to 30, I think 28 or 27.
Okay, so maybe we can wait a couple more minutes if that's okay. In the meantime, let me share my screen, just make sure it works. Can you see my screen? Okay, thanks for the thumbs up. And yeah, the only thing is I only have one monitor. Once I share the screen, I lost sort of the biggest screen to see all of you. So it's 5 minutes past the hour. Maybe I should start if that's okay, while more people may be joining shortly. My name is Kei Chong. I'm a professor at the Department of Emergency Medicine, also affiliated with Yale Center for Medical Informatics. And I also have joint appointment with the Veterans Healthcare, the VA Medical Center in West Haven. So I've been interested in database research, as you can tell from the title. I started my database research in the genome science area when Human Genome Project started in the early 90s. And also at that time I was doing my PhD database research. So my dissertation has to do with semantic data integration in the context of human genomes. And that's where I started. And later on, for my academic career development, I sort of continue to develop more and more databases in not only bioinformatics, but also neuroinformatics, and more recently, patient database or electronic health record. So that's sort of my path of database research and development. And today I'll talk more about the design and some basic development in the bioscience domain. So I don't know how many of you have used any database before. Maybe you can raise your hand or tell me a little bit, share your experience if you can. So get to know you a little bit. Anyone want to tell me or tell others whether you have any database experience? Or any one of you have used database like MySQL, Oracle, that type of database? No? But that's good. So this is what we can learn more about what are those databases. Of course, I mean, when you talk to different people, they may give you different definition of database. Some people may say Excel spreadsheet is a database, or files, a database kind of, system. Yeah, I think it's true to a certain extent, but the database I'm talking about here is more related to relational database management system like Oracle or MySQL, just I mentioned. So let me start. I mean, as many of you know, we are getting more and more into this data-intensive scientific research and discovery. That's what we call the fourth paradigm. This is sort of the pioneering vision proposed by Jim Gray, who is also called or known as Mr. Database. So starting in 1970s into 80s and even 1990s, so Mr. Gray sort of is one of the pioneer in database technology because he saw this data movement in life sciences or even medical sciences. So he has this vision as we collect and need to deal with more and more data. So database or database system play an increasingly important role in how to use database to manage a large amount of data, scientific data in this case, more efficiently and seamlessly. So that's the early vision of Jim Gray, and he loved to sail, as you can see in the picture. But unfortunately, in 1997, when he drove his yacht off the shore of San Francisco to a remote island, he just lost in the sea and was never found. So it was quite a mystery. A large-scale search was conducted, but his body and his yacht was never found. So he was pronounced dead in Abshire, in 2007. So his life ended kind of tragically, but his legacy remains, especially his contribution to database research. He actually had received this Turing Award, one of the prestigious computer science award, in 1998. So this is, the recognition of his contribution in the computer science field. And even earlier, right after the Second World War, this person, Vannevar Bush, who was the, I think, the chief officer of the Office of Science, American Science Development. So he coined this term mimics. Actually, this mimics is what today's database is, the same concept. So at that time, Mr. Bush envisioned mimics is a device in which individuals can use this device to store all his or her collection of books, records, or even communications, and can retrieve the information in a very efficient speed to sort of see what kind of information of interest can be pulled out from this huge collection using such a device he called mimics. But nowadays, this mimics is implemented in using a relational database system. So just to give you a context, the emergence of database, the significant role of database play in today's data-driven scientific research. And feel free to stop me if you have any questions. As you may already know, today we are dealing with large amounts and large varieties of scientific data. both healthcare and life sciences. Just name a few, or you can see a few pictures here, from drug related data all the way to genes or deep sequencing data to sort of mobile data. Each one of us has smartphone, which can now act as a personal healthcare device, for patient-centric health information. Each person can collect a lot of how many steps a person walks each day, or even heartbeat, blood pressure, all in a single mobile device like your smartphone. And such information can also be uploaded as part of your healthcare record. So just want to mention these 4 V's, which are the characteristics of today's healthcare and life science data, which is very high throughput because of all these high throughput technologies, whether it's a deep sequencing machine or mobile devices or MRI or PET imaging devices, all can be used to generate, text or binary data, structured, unstructured data at a high speed. And we already mentioned there are variety types of data, but not only that, but they are captured in different formats. Also, I mentioned structured data like, the relational database system you will learn more about is focusing on managing structured data. But also we have a lot of clinical text, for example, clinical documents that, contain a lot of useful information that, we may need to pull out and put it back in the structured databases. So that's why a technique like natural language processing can be applied to process unstructured data to make part of it become structured data that can be stored in database. And velocity, as you know, especially mobile data streaming, so on a second by second or minute by minute basis. So you really can collect huge amount of data at great speed. Last but not the least is the veracity of such, a large amount of data. Yes, quantity, of course, is one of the big challenge, but also another challenge is quality, data quality. So that has to do with, trustworthiness of data, especially patient data or some of the biological data. So how you can verify the data you generated are correct and of high quality. So we need to worry about, the quality of data, not just the quantity of data. So those are the 4 V's characteristics of today's healthcare and life science data. So just want to show you this annual special issue on molecular biology database published by this nucleic acid journal, NAR. So every year they encourage database researchers or developers to submit papers describing their publicly accessible molecular biology databases. So this journal, this special issue has started in the mid 1990s up until now, and you can see the growth curve is really exponential in terms of the number of molecular biology that have been developed over the past 2 decades. So you can see from just a dozen now, you have nearly 2,000 molecular biology databases, and each year you have pretty steady number of new molecular biology databases developed. So this is just a very kind of narrow field in molecular biology in one journal. And you can see there are already over nearly 2,000 publicly available molecular biology databases available. And you can imagine, other types of databases, whether in the public domain or in the commercial domain or whatnot. I mean, you can imagine, the number of databases that are available today. So just go a little bit deeper if you are interested in reading this special issue you can go, to the NAR website and sort of browse through the different categories of molecular biology databases. If you are interested in metabolic or signaling pathway, you can open that category and look at what databases have been published and are publicly available, like Reactome. Some of you may be very familiar with. To go there and download, maybe the whole Reactome data set if you're interested in signaling pathway type of data. Well, database is an engine, is what we call the back end. Okay, so that's what we are talking about more today. But you also need to develop a nice front end for regular users to access and retrieve information from your database. So in the 2018 special issue, they specifically highlighted this the Flavor Network database because they were impressed by this type of simple graphical interface front end to the back end relational database in this case. And you can see with this type of visualization of network connecting different types of food, sharing the same flavor molecules. So this is an easy way to integrate information within the same database. So the connection here is the common flavor molecules. And you can see egg is linked to, for example, yogurt in this case, because they share some flavor molecules. And you can click on a particular food to get more detailed information. So this is very intuitive point and click type of interface without requiring the user to learn a specific database language, which I'll talk a little bit more later. Any question? So what is not a database? I just want to address the earlier question I have to you. So just a file, whether text file or binary file, in our case is not considered a database because a database is more than a file. Of course, the underlying physical implementation of a database, involves a collection of files that are related to one another. It's also not just a Excel spreadsheet. Many of you have used Excel spreadsheet or Google spreadsheet. So a relational database is more than a spreadsheet. It's more powerful than a spreadsheet. In what way? So a relational database is really a collection of related information. So I want to emphasize related information because sometimes it's hard to relate information across multiple spreadsheets. But the purpose of a relational database, of course, the term relational may be a little bit confusing. It's not just a relationship, but also mathematical or relational algebra that I'll talk a little bit more about. But anyway, a relational database is really a collection of related information that can be easily accessed, managed, and updated. So those. So that's sort of the informal definition of database. And here I just want to give you a quick contrast between a spreadsheet and a database. For example, many of you use a spreadsheet for data analysis purpose or mathematical calculation, and also Excel spreadsheet is good, at creating chart or displaying chart or display some graphical data. A relational database system, on the other hand, is much more scalable. If you really have a large amounts of data set or multiple such large data sets, it's much more efficient to query using a relational database system. So a relational database system is really good for querying and structuring data in an organized way. And also a relational database management system can support large number of users who can simultaneously access the same database system. Whereas, even you use Google spreadsheet, yes, you can collaborate, but still, it's smaller scale, and it's really hard for multiple users to access multiple, even Google spreadsheets, in a way that won't, affect one another. But relational database system have this concurrent data access protocols, so it's all seamless and transparent. So you really don't have to worry how they do it behind the scene. But the thing is, it always guarantees correctness of and consistency of data, even multiple users access the same database table, performing different database operations at the same time. Last but not the least is the scale. Even a single spreadsheet, yeah, you can use it to store maybe tens of thousands of rows, but you have tens of millions of rows. If you have hundreds of tables, spreadsheet won't scale, but a relational database is quite scalable. Yeah, so just some numbers for your reference. So next, I would like to talk a little bit about some key database concepts that I want you to be aware of. First is data integrity, which is the assurance that data are correct and consistent all the time, not just sometime. Data in this case reflects the real-world objects like a gene, a protein, an experiment, etc. Data redundancy. It occurs if data are duplicated between files. Sometimes, data redundancy cannot be it's hard to control because you have multiple users, especially if you use spreadsheets, you may find redundancy in the same spreadsheet, even managed by one single user. But it's important, not let this type of data redundancy cause a lot of errors or troubles in your data analysis. And data dependency, of course, we are talking about, different real-world objects really have a relationship dependency or interdependency with one another. Like a patient can be treated by a doctor at a certain medical center. So all these different types of entities really relate to one another in some sense. So we need to also worry about, when we enter data, which table we should enter first before entering related or new information in another table, because they are related or depending on one another. If you are dealing with patient data or healthcare data particularly, you have to worry about data security. Like I mentioned at the beginning, I have a dual role at Yale dealing more research type of data. So data security in that case is not that important or significant. But when I'm working at the VA dealing with veteran healthcare data, it's a different world. It's a very secure world. Everything is behind the firewall. And I can, nowadays, during pandemic, I can work from home to access VA data remotely. I don't know if you can see, this is my VA V card I have to use to access VA data. But if I travel to another country, I wouldn't be able to access such sensitive information. So data security is very key in dealing with patient data. So what is a relational database or SQL database? The term SQL or SQL stands for Structured Query Language, because relational database is a standard, industrial standard. One key standard feature is this common query language called Structured Query Language, or SQL. So that's why relational database system is also called SQL database system. So let's start with relational data model, which is sort of like an abstract data model based on set theory or relational algebra. It was first introduced by Professor E.F. Card in the early 70s. And a relational database management system is an application of software implementing the relational data model. So from this abstract data model, we have a physical implementation of that data model. That becomes a relational database management system. Examples include, I already mentioned, MySQL, Oracle, and if you're a Windows user, Microsoft SQL Server is pretty popular relational database management system. In the VA database system, they use Microsoft SQL Server. even though they have different database vendors, but all vendors support the same SQL language. So the SQL query language is the same across all this database management system. So finally, relational databases have been widely used to manage data in different domains. So I started, relational database work in the human genome area, and nowadays I continue to do relational database development and research in the context of VA patient data, for example. So what are some of the key components of a relational database system? First of all, a relational database system consists of a collection of related tables. In the formal terminology, a table is called relation in relational algebra. So a table of relation represents some class of real-world objects like patients, drugs, hospital, etc. Each table or relation consists of a set of columns or attributes. And when you have populated the table, of course, it will consist of rows, just like an Excel spreadsheet. But in relational a model or algebra, they call each row a tuple. So each column or attribute corresponds to some attribute of a real-world object represented by the table. Like a patient can have social security number or some kind of system-generated unique ID, patient name, etc. So each row in a table corresponds to an instance of that object represented by the table. A patient table, of course, each row corresponds to a single patient, okay, who may have, social security number, address, name, etc. Now, when you have different tables representing different real-world objects, so how do we organize, the contents of this table and how to make sure they can link to one another in a meaningful but also consistent way? And to do that, first we need to know about this notion of keys. So each relational table has to if this is a good database design, each table should contain a primary key. What is a primary key? A primary key could be a single column like patient social security number or patient ID, or multiple columns. In this case, some people may prefer to use the combination of first name, last name, although that's not the best practice as the unique key for a unique primary key for identifying patients. So I already said it. A primary key is basically a unique identifier of a patient of a table row. Like the sample ID would be the primary key for the biosample table. So what is a foreign key? So primary key, foreign key link allow two tables to be related to one another. A foreign key is taken from a different table. For example, if you have the experiment table, the sample ID in the experiment table is actually called the foreign key to the sample table, because sample ID is the primary key in the sample table. So now you can see how you can use this foreign key, primary key relationship to connect two or more tables. So this is a simple student table, just have 4 columns, student ID in this case underline, which means it's the primary key. You have student name, address, and the major the student has, each student has. So now, in terms of organization of these database tables, I need to introduce this normalization concept. So this is different from machine learning or statistical analysis. It's not that kind of quantitative normalization. In the relational database, RAM normalization means how to restructure data in a way to minimize data redundancy. So that's what I just said. It's a process in which we can systematically organize columns and tables to eliminate anomalies due to data redundancy. So it involves decomposing a table into less redundant, smaller tables without losing information. So that's the principle that we need to apply. We don't want to lose data in the process of normalizing the database. The key objective is to isolate data so that all these database operations like additions, deletions, and modification can be made in just one table, and then those kind of updates can be propagated to other tables using primary key, foreign key relationship. However, normalization is a trade-off between data redundancy and query performance. Yes, normalization in general is a good practice in terms of database design to reduce data redundancy. That would help prevent anomalies caused by this data redundancy. But on the other hand, imagine you have one single table, although you have redundant data, but it's very quick to access that one single data table, even though it's very big. However, if you normalize that single table into 2 or 3 or even more subtables, now you need to join them together. And this kind of join operation in relational database sometimes could be quite costly in terms of speed. Especially you have very large tables. In the VA patient database, we have more than 6 million veterans in active duties, and then we have a lot of related information for those 6 million VA patients. So you can imagine joining tables in this type of database could be very slow when you need to generate report that require join of multiple tables. So we need to be careful. We need to be sensible in terms of normalization. But anyway, so normalization really, requires to make sure certain tables would be in a certain normal form. I'll talk about that in the next slide. So a set of tables free from certain set of modification or addition, deletion anomalies is said to be in normal forms. So what are different types of normal forms? So for this particular lecture, I will talk about the first 3 normal forms, which are very common in database design. The first normal form, the second normal form, the third normal form. The other normal forms is pretty rare. It's not very commonly used, but for the sake of completeness, for the sake of relational algebra, so database researchers come up with high degree of normalization based on some mathematical, theoretical, algebraic kind of approach. So what is first normal form? Each column values must be a single value. So you cannot have, I know sometime in Excel spreadsheet, I have seen you have comma separated values for certain columns, right? Like lists of gene synonyms. So you have a gene alias column. So oftentimes people put in, comma or semicolon to separate all these different genes alias. But in a relational database table, that is not recommended. You better split it into multiple rows. So each column name must be unique. So that kind of, a common sense. And you don't want to have the same 2 columns have the same name causing ambiguity. Since relational database is based on relational or set theory, the order of attributes or columns is insignificant. It doesn't matter. So as the order of rows, when you enter new rows into a table, really the order in which you enter these new rows doesn't matter. However, no 2 rows should be identical. So you don't want that type of ambiguity or redundancy occur in a database table. If you meet all these criteria, that table would be in first normal form. Okay. So this is the same or similar student table you have seen. So this simple table meet all the criteria you just saw. So this table, although it's not the optimal design, but still it is in first normal form. So what is second normal form? So you want to design, a little bit better to go a little bit further to reduce data redundancy, as much as possible. So a table is in second normal form if it is already in first normal form, and if all its non-key columns are dependent on the primary key. A table is in second normal form, it is free from partial key dependence. So you don't want some case, I mentioned before, a primary key can consist of multiple columns, right? First, for example, in the patient table, you may want to have for example, the social security number, the first name, and the last name. So this is just hypothetical. So those three columns would constitute the primary key of this patient table. Now, the social security number may uniquely determine other columns in the same table. So you don't want that type of partial key dependence to occur in the table. So that's why it's always a good practice to only have one single column as a primary key to avoid this type of partial key dependency. And would be even better if that primary key is system generated. So it's randomly generated, but guaranteed to be unique. So tables that have a single volume for primary key already set are automatically in second normal form. To achieve second normal form, we may need to split a table into multiple tables or subtables and match rows between this table using primary key, foreign key link. So the same student table you saw earlier can be split into these two smaller tables. So the first table is the student table. Each row corresponds to a unique student. So each student is recorded only once in the student table. And then you have a related table in this case, which is the course enrollment or major table that you can see which student has enrolled in which subject. Like Adam is enrolled in biology. And this in this enrollment table, the first column, the enrollment ID is the primary key. Okay, so this type of tables are said to be in second normal form because we, try to meet all these criteria posed by the second normal form. And last but not the least, if you really want to go another step further to make your database design more optimal in terms of eliminating data redundancy, you can go to the third normal form. So what third normal form says is every non-primary key column must be dependent on the primary key, and there should not be the case that a non-primary key column is determined by another non-primary key or this transitive dependency. To make it simpler, easier to understand, so I just use this student table. In this case, I just show you the columns of this student table, like ID, date of birth, and address information, including city, state, and zip code. Now, you can see the zip code here actually can be used to uniquely identify city and state, right? As we know, city and state can be uniquely identified by the zip code. But at the same time, ID is the primary key for the student table. So in this case, you have a subset of columns in the student table which are uniquely determined by the non-primary key column, in this case, zip code. However, the student ID can also be used to identify, to determine all the other columns in the student table. So you don't want a table to have a sub-primary key, zip code in this case. So we really want to remove this type of transitive dependencies by, again, separating this student table into two tables. One is the student, which only contain the zip code without the city and state, and the address table will be separate by having zip code as the primary key, and city and state information would be stored in the address table instead of in the student table as indicated in the original database design. Question? So if not, so now I want to talk a little bit more about a database design and how to ease.
Okay. I I don't think I completely understood the difference between the second and the third. Could you go back one slide, please, for a second? Right. So, in this, so if you go to the second normal form, the slide just before this, right, where you were showing the example,
Oh.
yeah. So in this, what you're saying in the first table, the primary key is student, and in the second one, the primary key is enrollment ID. Is that what you're saying?
Yep.
And it is linked via student. So the second table is actually linked to the first table via student, right?
Right.
So I don't understand how that scenario is very different from the example that you just showed us in the third normal form. Because if you were to go to the third normal form, right? What you're doing is your first table, in this case, like if you were to just compare it to the last example, the second table is the student table and the first table is the address table, right? So it seems the same. I can't make the difference between
Yeah.
it.
I mean, I think the product is the same after you normalize it, the tables. In this case, the original student table. Of course, they structure differently. So I think the key is really that third normal form. We are looking for all these transitive dependencies, and we identify a transitive dependency because a zip code in this case cause this issue. You have transitive dependencies. So you have a primary key and a subprimary key for a subset of columns. So that is this type of issue identified in this table. But in the previous table, you don't have this type of issue. So you don't have this partial dependency as
Got it.
in this column. So I think that's the key difference. Yeah, I agree with you. The look is the same. I mean, it's still two tables. It's primary key, foreign key. But I think is during this I mean, it's in the original table. You have to look back in the original table whether the original table have this type of partial key dependency. If you have this type of dependency, if you eliminate such a dependency, the table will be is set to be in third normal form. So that's the difference, whether you have this partial key dependency.
Sounds good. Thank you, Doctor.
Yep. Right. So I think yes, you can write SQL to create a relational database, a new database, and a set of new tables, and defining for each table the columns and the data type for each columns. So you can all write out by using SQL. But I think to make the database administrator developers life easier, so people have come up with this type of a model called entity relationship diagram, and implement this diagrammatic model using application and software. And database developer can use such software and application to develop relational database sort of graphically. So what is the sort of like the graphical model of this relational database design, or ER diagram? So it is a diagrammatic model proposed by Peter Pan after E.F. Card introduced this abstract relational model. So he came up with this diagrammatic representation of the relational model. So basically, this model describes the attributes and the relationship between the entities. So it goes beyond a primary key, foreign key link, which is not that meaningful, because you really don't have this meaning of relationship between primary key, foreign key. So it's just like two keys, which could be two numbers that happen to be the same, and then you connect them. But relational data model doesn't require you to specify what is the meaningful type of relationship exists between this primary key, foreign key pair. But in the ER model, it asks you to explicitly specify the type of relationship by assigning it with a meaningful human readable label. So database developer use this type of diagrammatic model to perform data modeling and explain the diagram to stakeholders like biologists, like clinicians, like biomedical researchers who may not understand SQL, who may not understand relational database design well, but when you show them a picture, it's really worth 1,000 words. So the key components of entity relationship diagram include entity, which represent a collection of objects in the real world. It's the same as relation, right? But they call it entity in this diagrammatic model. And each entity can have a set of attributes, just like a table has a set of columns. An attribute is a named entity or characteristic of an entity. And relationship, which is treated as first-class citizen in this case, is explicit, is meaningful, is an association between instances of one or more entities. And now we go another step, into the relationship to specify relationship cardinality. So we really want to express in this model the minimum and maximum number of occurrences of one entity for a single occurrence of another entity. So you have this one-to-one, one-to-many, or many-to-many relationships. So this is a ER diagram, an example ER diagram. So you have entities such as patient, physician, the medical procedures a physician perform on a given patient, and you can see the relationships are represented in using these diamonds. Like a patient is treated by a physician, and then you can see there's an end-to-end, many-to-many relationship for treatment. As you can imagine, a single patient can be treated by multiple physicians of different specialties. And on the other hand, a single clinician or physician can treat multiple patients. So that's many-to-many relationship. And each entity is represented by a rectangle, and each entity can be associated with one or more attributes represented by oval, circle. All right. So now, how do we draw this? Of course, we can draw it using pencil and paper, but that's not. I think it's a good start. Even today, I sometimes draw on a piece of paper the ER diagram of a of a part of a database, for example, to show it to user. Does it really mean this model makes sense to the user or not? I mean, I still use that method, but more efficiently and in a machine-readable way. There are tools and applications available today to allow a database developer to create ER diagrams for a database system. And so let's see if I can do a live demo by clicking. Going to the Vertebello website. If you're interested, you can sign up if you don't already have an account. But when you sign up, I would highly recommend you to register as a student or lecturer. So it's free. And also for academic user, they provide more features than a regular user. So I already registered as a lecturer. So now I can log in using my email address and my password. Okay, I don't know what happened. But anyway, I created different folders, projects in this system. So I go to one of the folder. And I can create a new model. So in this case, I would create a new physical data model. So in this case, I name as a test patient database. So now I can map it to a given relational management database system. In this case, I can map the model to MySQL. I can start modeling. Okay, so now I'm brought into this canvas tool that allow me to create like tables, primary key, foreign key, links, etc., etc. In this case, I can create a new table. I can name, rename it as patient, and so now I can continue to so now I click on the table and can add new columns like patient ID. So in this case, patient ID would be a integer data type, and I check the PK box to indicate this is a primary key for the patient table. And now I can add more add more columns, like name. In this case, would be like a variable, a character type, string type of variable length. So in this case, maximum could be like, I don't know, 100. And I can add another field called date of birth. And in this case, it could be daytime field. Now, notice that, of course, they are not primary key. One table can only have one primary key. And also, this N checkbox here to indicate whether a certain column would allow empty or blank values or not. So if you check, so if it's unchecked, so that means it's a patient table can have a blank value for name. Of course, that should not be true. So really, you may want to check this box to not allow blank values to occur. And primary key, for example, cannot be blank. So it's already deemed, so you cannot check or uncheck it. And then you can create another new table called admission, maybe. Patient may be admitted to a given hospital. And then you can add new column. For example, admission can have its own primary key called admission ID. In this case, could be integer 2. And now you can select this relationship choice here to drag from the patient table to the admission table. Boom, you can see it created a foreign key for you automatically. And this, I don't want to do that. And this symbol here, this is meaning one patient can have multiple admissions. Okay, so this is a one-to-many relationship. Okay, so now I use this a tool to sort of quickly and quite easily to create two related tables. And now, if you want, I can export this. Let me see, to a SQL files. Okay, so now it converts this diagrammatic representation into SQL statements. So this is the default name. So now I open this text file. Basically, it's a text file. So these are the SQL statements generated based on the ER diagram I just showed you. Okay. So with this, now you can import it into MySQL to generate this empty database and start. Next step would be to populate each table with rows. Any question? So with this type of tool, it's really make a database design easier and more straightforward. So let me try to go back to my slide. Just give me 1 sec. Okay, so that's Vertebello. So now next, I want to talk a little bit more about the SQL syntax. So this is what we call the OLIP or online transaction processing, is to basically support basic database operation, including insertion, deletion, selection, and update. So now all these operations, when they are performed successfully, they must be so-called atomic, consistent, isolated, and durable, or ACID. Atomic means, if you have a set of insert or mix of insert, delete, update operations, after all these steps are done, it's either the whole transaction is done, or the whole transaction involving multiple steps would be aborted. So nothing in between. So that would help prevent data corruption. Now, consistency, again, you have to, after you successfully perform a database operation, which may involve a series of database operations like this. So the results of that has to be consistent. The data sets after these transactions has to be consistent. So that would not be any errors occur. Isolations. So as I mentioned before, a database system can support multiple user access. So when one user perform one set of operations or one transaction, it shouldn't affect the other users performing another set of database operations at the same time. So the database system help coordinate that and make sure those two set of operations are isolated, not affecting one another during their independent operation. And durable. So the results of a database transaction has to be durable, has to be persistent. So that means it won't get lost, over time. So it has to be there all the time. So structured query language, as I said before, is an industrial standard, particularly is ANSI and ISO standard. It's internationally recognized. So this is a simple example of how to use the create database and create table SQL statement to create an empty database, to create an empty table. Just like what I showed you before, how to create a patient table. So this is actually how you can write a create table statement by specifying ID, name. Each column has a specific data type. And once you create an empty table, of course, the next logical operation is to insert records into this table. So this is one record, to be inserted in the patient table. And then you can issue a series of insert statements like this to enter multiple rows into the patient table. So now, over time, you may need to correct or update certain information in the patient table. For example, if you need to change the age of a given patient, so you can do that by update this table, set a particular column to a new value based on a given patient ID. So this is the row. The first row will be affected. The age will be updated or corrected. So now you can perform delete operation. So you can, if this patient die or no longer needed in the system, so you may remove this patient record. In this case, based on the name, to remove that row. And you can retrieve, select certain rows, a subset of rows from the patient table by specifying which columns you want to display in the query output and query criteria. In this case, I want to find all the patients whose age is greater than or equal to 40 years old. And then I can sort the results, the output, by the age column in ascending order, for example. So those are the rows that meet the criteria. So now, sort of like Excel, you can use a relational database to perform some kind of aggregation function. In this case, I can use the average function to calculate the average age of patients and group by sex. So in this case, I could use this SQL statement, use group by option to calculate the average age for female patient and for male patients. And this is the query output. So now I can do more complex SQL query by issuing a join between two or more tables. So in this case, I join the patient tables with the lab test table, and I use A and B as the alias for each table to make it a little bit shorthand in terms of writing out the SQL query, because otherwise, I would be writing a very long verbose query. So this alias method is allow me to use shorthand notation for identifying tables. So I can select all the columns from the patient table and only the report text column from the lab test table by joining the primary key and foreign key between these two tables. So this is the syntax. Inner join means matching the same values between the primary key and foreign keys between these two tables. So there are other types of SQL statement. In the interest of time, I won't go into this statement, but you can learn more about it yourself if you are interested. And one thing of note is that if you are doing join query or querying a large database, so you better create a so-called index for certain table columns. For example, for primary key and foreign key, they are automatically indexed. So the speed of joining should be boosted based on this index between 5 primary key and foreign key. But you can also index other columns like the age column of the patient table. If you happen to query the patient table by age quite often, then it's recommended to also index the age column in this case. So, and finally, I want to talk about OLAP. So I mentioned OLIP database, which is supporting this type of basic database transactions involving update, deletion, addition, selection, etc. But OLAP, on the other hand, means online analytical processing. It's just like you use database to do some kind of analytical queries instead of transaction-based query. So it's more like data mining in this case. So OLIP databases, as you look at before, are tuned to relatively smaller or medium size of database with pretty relatively straightforward queries, even though it involves complex join in some cases. But some application use fewer but more time-consuming analytical queries. In this case, new database structure or architecture is required to handle such kind of analytical queries efficiently. So now, instead of doing a lot of normalization, so to create a OLAP database, or sometimes they call it data mart or data warehouse. So that means it's not transaction-based anymore. Typically, a data mart or data warehouse is created based on existing databases. And assumably, these existing databases are transaction-oriented databases. Now, when you integrate them to create a single huge data mart or data warehouse, so you don't perform update directly on such warehouse or data mart. Instead, there are batch processing behind the scene that would periodically integrate the underlying databases to update the data warehouse or data mart, which in turn support analytical queries efficiently. Like Amazon or Walmart, they each have their own data mart or data warehouse to support data mining or analytical queries. For example, Amazon can use their data mart to help analyze purchases by customers to identify products of likely interest to customers. Walmart, in another case, can allow analysts to look for merchandise items with increasing sales in some regions. So this are two examples of analytical queries which cannot be efficiently handled by traditional OLIP databases. In the VA database, for example, I work with is an example of a data warehouse, a patient data warehouse, or patient data mart. So what do I mean by that is, so this is the basic database design or structure for a data mart or data warehouse or dimensional database. So basically, everything is collapsed into a one single central fact table conceptually, and there are dimension tables, and each dimension table can be linked to the fact table by a foreign primary key relationship. And I'll show you an example. So this is a example of a data mart or data warehouse using this star database structure or dimensional data structure. So at the center here, the center of the star, you have this fact table, basically contains foreign keys to the other tables, the dimension tables. So you have patient ID as the foreign key to the patient table, provider ID as the foreign key to the provider table, and then you have additional dependent attributes to describe additional information like the date, the comment. So for example, for each patient and provider pair, this table may contain information about particular clinic visit involving a pair of patient and clinician. So you may want to record the visit day, the clinic visit day, and additional information like the diagnosis, what kind of diagnosis made by a given clinician on a given patient, on a given date, on a given visit day. So you can have, diagnostic information capture as well. So this is just one, simple example, show you how to collapse, a traditional big, analytical, OLIP database into an OLAP database with this type of structure. So once you have this type of star structure, I just want to show you, in the interest of time, conceptual query without getting into the syntax of the SQL queries. Some example analytical queries, two in this case. So one analytical query can be to compare number of patient visits across different clinics for a given year, and then the second analytical query is to identify the top 10 most performed medical procedures among all clinics from 2010 to 2014. So believe me, if you want to perform this kind of analytical queries using the traditional normalized database structure, it would involve very large table drawings, and the speed of this type of query would be very slow in a traditional OLIP database. But if you transform the OLIP database into a OLAP database structure, this type of analytical queries will be much more speedy, and the performance would be very good. Okay, so now so this whole lecture focus on relational database or SQL database, but there are other more modern database technologies. I just want to mention, like NoSQL is the non-SQL database technology, including graph database or document database like MongoDB, and then you have semantic web, which is sort of the knowledge base. It's go beyond data information, but knowledge representation. So with that, so that's the conclusion of this lecture. I know it's time